Okay, so the plan for today, pretty straightforward. Just continue on with the Chapter 2 PowerPoint. Um, if we have time at the end, we'll do a quick intro to Excel, working through a couple of Excel spreadsheets. If we don't have enough time at the end of today's class, then we'll do that first thing next time, probably. So just a reminder, if you're a little bit nervous about Excel, if you haven't seen it before or opened it or used it at all, if you want something a little more structured, there's the Coursera course that's linked in the Useful Websites tab. That's a third-party site, so it's not a CCAC site. It's not something official for the course. Um, and note that like Coursera will ask you to pay for it, but there's usually a small link somewhere. They kind of make it pretty small, but it'll say something like audit this course, and you should be able to click that and get into the course for free. You won't get like a certificate of completion at the end, and I think some of the things like the ability to take tests or like um, to submit projects for grading and for feedback and all of that won't be there, obviously, because that's the main thing that costs them money. Um, but you'll be able to, work through the material and the video lectures and stuff if you want something a little more structured, that's a little more like a miniature class on how to use some of these basics of Excel. You don't need to be a power user of Excel. You just need a few basics. And if you're cool with, just kind of following along with what we do in class, using the information that's in the textbook, that should be plenty of material to get you what you need for the course. But again, it's a little less linear, a little less structured because we're kind of learning some Excel things whenever they pop up, whenever they're useful for us in stats. So if you wanted something a little more linear and kind of self-contained, the Coursera course is great, but also just using Google as a reference. I think that's just a general um, good thing to learn and as a general rule, especially these days, if you need to know how to do something, whatever it is, whether it's something on Excel or whether it's how to check the oil in your car or whatever, um, being able to get comfortable using Google as a reference and searching for something or looking something up on Stack Exchange or whatever it may be, or using YouTube. um, how do you go out and kind of figure out how to do something that you don't know how to do uh, when it's not like, in the next section in the textbook, something like that, when it's not, kind of handed directly to you. Um, I think that's a little bit, that goes a little bit along with the idea of being a lifelong learner. Um, so I think that's just a good skill to develop in general. And I mean, Microsoft Excel is a very widely used program. So if you just go to Google and you type in, Excel, how to compute average or something like that, you'll come up with lots of good high quality resources right away that will help you with that. So, all right, so that is the plan for today. And our quote of the day today is, well, it's kind of a meme. It's a comic from this group, I guess. I don't know what you call them, a publisher or something. XKCD. Uh, they publish comics like this, the funny little comics that usually have something to do with some nerdy topic like science or math or something like that. And in this case, I forget the name of this. I think it's maybe called Goodhart's Law, but the person on the left says when a metric becomes a target, it ceases to be a good metric. And the idea behind this law is um, if you tell your employees, let's say you're a management or a CEO or something, you tell your employees, I want this one number to look good. That's your target, right? This number is important to us. Maybe it's something like customer satisfaction, maybe it's whatever it is. The what you're incentivizing is for people to destroy the business to make that one number look good, right? You might use that as a metric to say, how are we doing in this area? But once you transition that to a target, and especially if you say your bonus or your job or something is dependent on this number looking good, well, they'll let the business crumble just to make that one number look good. So that's why you want to be careful of setting up an incentive structure like that. So when a metric becomes a target, it ceases to be a good metric. It's no longer really valuable um, for you to understand how well you're doing in that area because people just game the number. And the other person says, oh, that sounds bad. Let's offer a bonus to anyone who identifies a metric that has become a target, thus making metrics that have become a target, that would ideally be a metric as to how you're doing in this area, but that makes it a target. And so people will then identify lots of metrics that have become targets, even if they're not actually metrics that have become targets. So it's a little meta, as they say. Um, One kind of like funny example of this, and there are kind of several variations of this that all sound very similar. So I don't actually know if this ever actually happened or if some of these are like fables and some of them are true, but the story goes something more or less like there's some infestation of some animal, let's just call it rats, in some area, and the local government says, okay, we need to get rid of these rats. So we'll tell people, all right, if you trap a rat and bring me in a rat tail, essentially proving that you killed the rat, we'll give you $1 or something. We'll give you some amount of money as a reward because we want people to trap these rats, kill them, and then um, and then we hopefully will reduce the rat infestation. Uh, but then people realize that, wait, if I breed rats and then kill them and sell them, then I maybe what I can sell them for is worth more than what it costs me to breed them. So you end up with more rats because people will breed them and then sell them because it's easier to breed them and sell them and still makes them money than it is to catch them in the wild. And of course, if you get good at catching them in the wild, then the population goes down and it gets harder to catch them in the wild. So that's a classic example of this, right? Um, yeah, that this kind of idea of setting up an incentive structure that maybe at the surface level looks like a good idea, but really people just kind of game the system to make that one number look good, like the number of rats killed, and it's not actually targeting the thing that you want, which is the number of infestation rats, if you want to call them that, killed. So, all right, so that's the thought for today. Let me reorganize my windows here for 1 second, and then we will jump back into things. Give me 1 second here. All right, I think we got everything set up now. Um, so, like I've said before, I'm in full screen mode now, so I don't have chat showing. So if you have a question or wanna add something, you can just unmute yourself and speak up. That's perfectly fine. But if you pop it in chat, I might not see it. All right, so continuing on with the Chapter 2 PowerPoint. And I just want to really quickly recap what we talked about last time. So we're moving into chapters 2 and 3, talking about descriptive statistics. And the idea here is we have raw data. We might think of a data set of like 100 or 1,000 data points, some large data set. Practically speaking, in class, we'll be working with smaller data sets, but we kind of imagine this being more useful for the larger data sets. And the goal is to crunch that large data set, that say maybe 1,000 pieces of raw data, that if I just look at this page of 1,000 numbers or 1,000 letters, whatever it may be, I can't make heads or tails of it. It doesn't really help me at all. But can I maybe crunch that down? Can I maybe make a picture out of that? Can I maybe crunch that down to a number like an average uh, that I can look at and I can understand more easily? So that's the goal of chapters 2 and 3. And chapter 2 specifically looking at the pictorial, the graphical side of things. What are some graphical representations of data sets that can help me to understand some characteristic of them? And then chapter 3 looking at numerical descriptors, things like maybe computing an average. And we said, well, we have all this raw data, but probably the first thing we want to do before we try to jump into making, say, a histogram or pie chart is to actually just organize it. So we talked about making frequency distributions, for instance, taking these 25 data points and putting them in a frequency distribution like this with different classes and the frequencies, which are the counts, the number of individuals who answered A, B, C, D, or E. We might have to group in some cases in order to make the number of classes reasonable. Or sometimes we have a small enough number, even if it's kind of a numerical scale that has some natural ordering or ranking. Sometimes we have a small enough number of possible results that we just kind of treat it like categorical, but we do want to respect that ordering. So I'll list the responses here as 1, 2, 3, 4, or 5 stars for whatever how satisfied they are, and the number of respondents for each of those. Okay, so that was just a really quick rehash of what we talked about last time. And from this point forward in this chapter, we'll kind of presume that we've done that organization step already, that we have the data organized as some kind of frequency distribution or table. And then the next step is to somehow make a graphical representation. So what are some examples of graphical representations of data? Well, I think the most ubiquitous one is the histogram. Histogram, bar chart, column chart. It's called a lot of different things, but uh, those words all essentially refer to this same thing. I think there are some nuances like whether the bars go vertically or horizontally, or whether they touch each other or don't touch each other, but they all really reference the same idea. So histogram uses a bar graph like the one below that visually represents the frequency. So you see that across the bottom, across the horizontal axis, we have indicated the grade range, the different classes or bins, 0 to 59, 59.5 to 69, and so on. And on the horizontal direction, we have the number or the frequency, the number of results that were in each of those bins. So 0 to 59, we saw 5 results there. 89.5 to 100, we saw 9 results there. There were 9 A's, for instance. Note that in a histogram, we do occasionally have, let me jump back to this one here. We see that there were 0 D's, 0 folks in the 59.5 to 69 bin. We do leave a space for that. That's essentially just a bar of height 0. We don't, we don't get rid of that class just because nobody was there. It is important to leave that space there. So we see 0 individuals in this class, 59.5 to 69. For instance, 6 individuals in the 69.5 to 79. So we can tell kind of at a glance what the distribution of grades looks like. It looks kind of slightly uniform. There's kind of a smattering of folks all over the board, except there seems to be maybe a preponderance of A's and not many D's or no D's. Right, so I can tell that really quickly looking at this graph that there seems to be about an equal number of B, C, and F, more A's, no D's. I can tell that really quickly compared to if I was just looking at these 25 numbers. It will be hard to make heads or tails of what these grades were. And you could especially imagine if instead of having 25 numbers that I was looking at, if I had 250 or even 2,500 numbers, the effect would be magnified, right? The picture would be just as easy to understand what proportion of students, say, across 10 years of stats classes or something got what grade. The graph would be just as easy to understand, but the raw data would get unwieldy very, very quickly if it's not already at 25. And this is just showing a different example of a histogram. We could have a histogram with the bars not touching each other. I think they might call this a column chart, but again, we'll just use those words interchangeably. And this is the survey, customer satisfaction survey response data. So we see responses of 1, 2, 3, 4, or 5 for how satisfied were our customers, and again, on the vertical axis, the number, the frequency. So in a histogram, vertical axis is always the number or frequency, or maybe something closely related to that. And the horizontal axis is the class. So the vertical axis is always counting. It's always kind of has the feel of a discrete quantitative. Uh, I don't want to say variable. I guess variable isn't a terrible word, but a discrete quantitative variable, more or less. And the horizontal axis sometimes could be quantitative, like this response data, right, where there's a natural ordering or ranking, but it could also be qualitative. I could have just as well made a histogram of the favorite beverage. So the class listing, or in this case, the horizontal axis, doesn't need to be numerical or have an order or anything like that. But my frequencies always will, because my frequencies, I'm counting the number of data points that are in each bin. So here's a little, again, a funny XKCD comic. I actually forgot this was in here, so uh, I'm not like trying to hard sell XKCD or anything. I just happened to pick this quote for today, and uh, this comic was in here. But uh, trustworthiness of information by file extension, you can see the bar chart here. If it's written in tech, which is kind of like a mathematics typesetting almost language, um, probably pretty trustworthy. If somebody knows enough and cares enough to write it in text, it's probably going to be right. PDF, same kind of thing. If it's information presented in a GIF or a JPEG, or if you want to pronounce it incorrectly, you could call it a GIF. Then then maybe not so trustworthy, right? Um, so just a joke, obviously. And I'm happy to see that Excel is kind of somewhere in the middle here. So if you set up a spreadsheet, you know, it's maybe more likely than average to be correct information. Obviously a joke, right? Or it's just a silly comic. All right. Here's another kind of nice example. I thought this was a really good example of using a bar chart like graph, or a histogram like graph. So here we have the 50 US states plus DC. And we look at the top right here, and there's a legend that says annual percentage change in population growth. The higher the growth, the more red the bar is, or a decline, the darker blue means the greater decline. And what I like about this is it combines the idea of kind of a histogram. Now, I should say this isn't really technically a histogram, because these bars represent growth or decline, say percent change or something like that, year over year. So my horizontal axis really is time, and my vertical axis really is percent change. But I'm showing this because it shows an example of how you could maybe use the idea of a histogram in a slightly different way. And I think this is actually a really good graphical representation of data. So we just glance across the whole country, and we can tell at a glance, especially because they've used this coloring index, we can tell at a glance some things that just pop out to us. Does anybody notice anything that kind of pops out to them that they find interesting or unusual? There's maybe three or four things here. Any thoughts?
Nevada's pretty high. I think that's Nevada.
Yeah, yeah. So we see there was a lot of growth in Nevada, really kind of in the whole like southwest-ish area over here, Nevada, Utah. It's pretty terrible. Is that New Mexico or Arizona? I forget which one is which. Um, but kind of in that whole southwest area, we're seeing a lot of growth. Um, I think also in like Wyoming up here, there seems to be a decent amount of growth, which, I mean, when I think of Wyoming, I think of, not very many people there, but um, yeah, so yeah, there's kind of like a cluster of growth over here in the like not quite all the way out to the west, even in some areas like Idaho. But yeah, we see it most markedly in Nevada. So so that might be something. This is what was sometimes referred to as exploratory data analysis, right? I have no idea why there was a population boom in Nevada, but I see it in the data. Maybe I dig into it. Maybe I look at those years and, try to maybe do some Googling or some interviewing folks or whatever, and look into, I wonder why that happened. What would explain this data? Why were people moving to Nevada in such droves in that time period? Anything else that sticks out?
Louisiana has a really big decline.
Yeah, so that's maybe the one the one like big decline that we see. Overall, we see mostly slow and steady growth, like populations in general tend to do, just kind of, grow slowly and steadily. But Louisiana has one big negative year here. Any idea what that might be? This isn't necessarily a super current graph.
The hurricane.
Yeah, there was Hurricane Katrina that really devastated New Orleans. Um, Basically, everybody moved out and moved other places, and you see, for that year or so, while things were being, kind of fixed up a little bit, and you see that same year that Louisiana had a big drop. You see, like Texas had a bit of a spike that year, Georgia had a bit of a spike, Florida had a bit of a spike. Although, I mean, Florida was a couple years, so maybe it's a little less explained by that, but you see some of the surrounding states had spikes that same year that Louisiana lost a lot of folks. And then we see that Louisiana looked like it had, kind of okay growth the next few years, maybe as folks are starting to move back. Yeah, that's definitely something we see. Something that's a little less, um, you know, I don't know, like surprising. Well, kind of like the Midwest here, just kind of from let's say Kansas over to like PA, just kind of general slow and steady growth year over year. So kind of like the stereotypical Midwest, right? It's like, not really super surprising. Uh, we see some places like DC or Rhode Island had a change where DC was having population losses for a couple years and then some growth. Or like Rhode Island had some growth for a couple years and then some losses. Um, we look at somewhere like Michigan, it looked like they had a few years in a row of some sustained losses as well. So that might be something else we notice. I actually think that it's kind of interesting, not only looking at the data, but bringing in a little bit of kind of outside understanding as well. You look at Hawaii and it's like, yeah, Hawaii's population is growing. I mean, who doesn't want to live in Hawaii? But also like Alaska's population is growing, right? I mean, when I'm thinking of like of all of the states that I'd want to live, if I could just pick a state, I wouldn't think Alaska would really be on my radar, but Alaska's population is growing, over these 10 years and not insubstantially. So I think that's kind of interesting, why is that? Is there some kind of economic boom up there? Is there an oil, um, something to do with oil? Is there more oil up there, demanding more workers at high pays, Um, so it's kind of interesting to ask, what's going on there. Um, yeah, I think, and then I think also looking in the like Southeast, Florida, Georgia, those kind of areas, we're seeing kind of slow, steady increases. And maybe we can explain that with kind of the aging of the baby boomers, kind of either snowbirding or just moving south full time. That might be an explanation for it. But again, we might want to dig a little deeper. So we're not bringing too much of our just own personal biases and personal experiences to the table. And, if we were interested in one of these aspects, we might uh, think that we have a good idea what's going on, maybe dig a little deeper and see if that's the case or not. So I just really like this because when you think about this, 51 states, this is 10 years for each state. This is 510 data points presented in a way that just kind of with a quick survey, 10 seconds, 20 seconds looking at it, you can pick out, three, four, five, maybe interesting phenomena that maybe you can explain. In the case like Hurricane Katrina, it's probably pretty obvious that that's essentially the sole cause of that huge decline. And in other cases, like, the Vegas bump, I'm not really sure what that was. Maybe we can look into that. And this is just a more zoomed in version, just in case anybody was having trouble kind of seeing any of that. This gives you um, just a zoomed in version of what we were looking at that has, it's a cross section of those different things we were talking about. So for those more in the sciencey fields, My background is more in business and finance, but I like to throw some medicine and science in there uh, every once in a while for those folks going into those fields. If we look at the results of a GCMS, a GC mass spec unit, basically what it does is the gas chromatography separates particles. You put some fluid or something like that, some substance that you're interested in knowing what it is. You put it into this machine, and it forces that substance through kind of a porous medium. So it's not easy for the molecules to get through, but they can eventually get through. So you kind of like sort them by mass to charge ratio. You're kind of pushing them through with some gas or some charge or whatever it may be. Um, and kind of the bigger molecules get held up longer and they take longer to make it to the end of this tube. And the smaller molecules, or maybe the ones with less charge interactions, can move faster through the porous media and they can make it to the end faster. So the retention time up here is kind of like how long it took the uh, this component of the sample to get to the end of this tube. Are we looking at a bigger molecule or a smaller molecule? And then the mass spec is where they blast these molecules with electrons and blow the molecules apart, and through some, really fancy physics and engineering, and people a lot smarter than me build these things, they can tell um, that they can get a signature, I guess you could call it, um, of what this certain chemical looks like according to the mass to charge um, distribution down here. So we see that for each of these kind of bins of mass to charge ratio, 30, 31, 32, etc., there's lots of bins here. We see the certain signature. We see a couple of peaks, a couple of areas where there's a lot of frequency or a lot of sensor data, and a lot of areas where there's not really much sensor data. And the computer looks at this signature and compares it to a database of signatures of known chemicals and tries to match it up. And in this case, it came up with this molecule here, some kind of a ketone or something like that. So that's an example of, again, a histogram where in this case, we have like a ton of different bins, because we're really, the goal of this histogram, so to speak, is not so much for human digestion, but more for the computer to be able to match these signatures up. Okay. But as humans, we can look and we can see, okay, there's a couple spikes here, there's a spike there, not really much else going on. And this is kind of a similar idea, also GCMS, and this is for retention time. Here, our horizontal axis represents retention time in minutes, so it's more like uh, it's a little bit less like a discrete bin and more like a continuous variable almost. And I'm cheating a little bit here because this isn't quite a histogram. This is more like a line graph, but you can see that where these spikes occur, uh, these are different types of sugars that have these different retention times. Okay, but this kind of introduces the idea of a line chart. A line chart or a frequency polygon. I don't think I've ever heard anybody actually call it a frequency polygon. They just call it a line chart or a line graph. If we remember our grade range data, let me go back a couple of slides here. We had our FDCBA at frequencies of 50659. And we see basically the same thing here. We see our grade range, our classes, FDCBA, and here we put a point above each class at 50659, and we can connect them with a line, just connecting the dots with a line. If I have the type of data that I can use to construct a histogram, I can construct a line chart off of it. Why would I choose one over the other? Well, a histogram kind of gives the feeling that there's not much connection between one class and adjacent classes. On the other hand, a line graph, it kind of gives the feeling that there's some kind of inherent connection between adjacent classes. One really good example of a line graph is, let me jump, it's a little later in the Excel spreadsheet, but one good example of a line graph is something like, say, stock market data, where if I look at a stock price today, if I ask you to guess what the price tomorrow is going to be, if the price today is $50 a share, you're probably not going to guess $2 a share. You're probably not going to guess $200 a share. The price tomorrow is probably going to be about $50. It's probably going to be pretty close to the price today. So if I know something about the state of things in, say, one category, one class, the kind of next class, I have a pretty good idea what's going to happen. So that's, I think, the best use of a line chart. Here, I'm just drawing a line chart uh, to give you a demonstration. But I think for this data, I would probably opt for the histogram over the line chart, because grade data, like if I know how many D's there are, that probably doesn't give me a really good guess at how many C's or how many F's there are. I mean, it might a little bit in the sense that knowing what the number is scored in one of these grade ranges gives me maybe a sense of the size of the class or something like that, but it's not, I don't think, it's tied together. The number of students who got a D versus a C versus a B, I don't think is as tied together as something like, say, a stock price over time. So here's an example of a DNA sequence. So this is the output of a Sanger sequencer. If you're at all interested in medicine or science, look up how Sanger sequencing works. It's really a super interesting process. Really cool idea that Sanger came up with to sequence genetic material. And you see these different spikes, like this blue spike here, indicating a cytosine at that base, at that locus, or this red spike indicating a thiamine, a base of T at that locus, and so on. You see these different spikes over time. Each one of these colors represents something like intensity, or number of whatever sensor units at a different time going across here at what we're considering like the first base, the second base, the third base of this genetic sequence. And we really see that this is a chart with 4 line graphs on it. One blue line graph for intensity of cytosine. We see it's kind of high here. We made that call for cytosine, but it's low in the next one. That's a thiamine, not a cytosine. The one after that, the blue spikes again, and that's a cytosine there. We see off to the left, there's a little bit of, seems like things are a little befuddled here. And, there might be some spikes overlapping or something. Sanger takes, a couple dozen base pairs to kind of really get, to kind of hit its stride and get going. But we see that most of the time we see a pretty clear, one individual spike, and we can make that call for what the nucleotide is at that locus. And we really have 4 overlaid line graphs here in 4 different colors. So again, overlaying something like color on top of the basic structure can be really helpful. Then again, just a zoomed in version in case you were having some trouble seeing that in detail. And here would be a kind of a full read for somebody. So again, we see at the very beginning, it's really hard to make any kind of call because the peaks are all just kind of jumbled together. But after the first 20 or so bases, we can pretty confidently start making calls. Okay. Next up is, again, I don't know where people get these names, but an ogive. This is really just a cumulative frequency chart. Let's run back and remind ourselves what a cumulative frequency distribution is. So remember, we have our raw data. We can make a group frequency distribution out of it. We have one class that is the A's, and we have 9 people that got an A. We have 5 people that got a B, and so on. But a cumulative frequency distribution, I can look at the people who got, say an F or below, or in that case, just an F, the less than 60 class, there were 5 of those. And instead of setting up my classes or my bins so that they are like mutually exclusive and exhaustive, so when I move from one bin to the next, there's no overlap between the two and also no space between the two. Instead of setting them up that way, I'm going to take my original bin, my less than 60, and I'm going to make it bigger. So I'm going to accumulate potentially more frequency over time. I'm accumulating, that's a cumulative process. So next up, instead of looking at F or below, basically, I'm looking at D or below, less than 70 or 0 to 69. D or below, there were 5 folks that got an F and 0 that got a D, so D or below. I expand the F bin to include the Ds as well. I still only have 5 folks because nobody got a D. The the C or below bin, the next one up, I expand the D or below one more class width to make it up to a C or below. Well, there were 6 folks who got a C, so they get added to the 5 Fs and the 0 Ds. This bigger bin now has 11 folks in it, and then 16 and 25. Well, in ogive, or just the cumulative frequency graph, is really just the graph of the cumulative frequency distribution. So again, F or below, 5 of those. D or below, there were no Ds. So D or below, D or F, just 5. C or below, there were 6 Cs. So those 6 Cs get added to the 5 Fs and the 0 Ds, making 11 folks who got a C or below. So this is always an increasing graph. As we go from left to right, the graph can only go up, or perhaps stay straight on occasion. So that's a cumulative frequency graph. Another thing we could look at is, instead of actual frequencies, instead of numbers like 7, 4, 5, 3, 6, we could look at relative frequencies. We even talked about this before when we were making our frequency distributions, that we could present the data as a percent instead of an actual frequency, and that had some benefits. Now, the picture doesn't really look any different, right? Going from one slide to the next, the picture looks exactly the same, but the difference is this horizontal, or sorry, the vertical axis. If I'm presenting the frequencies, the vertical axis is the number of data points in each bin, 0, 1, 2, 3, etc. If I'm presenting the proportions, the vertical axis is the percent of all the data that are in each bin. The pictures actually don't look any different, but if I present proportions, well, on one hand, that can have some disadvantages. I might be really interested in actually knowing the numbers, right? So if I present this graph like this, or if you've ever seen those commercials that are like 4 out of 5 dentists recommend Sensodyne or something, apparently their marketing works really well because that popped into my head. But you kind of ask yourself, well, is that like literally 4 out of 5? Like you asked 5 of them and 4 of them said yes? Or is that like you asked 500 and 400 said yes? I don't know what the sample size here is. And we saw that was something that we want to be careful with when evaluating data and statistics is, well, what was the sample size? Is it large enough to be representative? I don't know that if I'm just looking at proportions. I do have a sense of that if I'm looking at raw data. On the other hand, if I'm comparing maybe the favorite soft drinks in 3 different cities, and I have, city A has a sample of size 400, city B a sample of size 100, and city C a sample of size 25, it might be a little more difficult for me to compare those numbers one to the other directly because, of course, I'm going to get a lot more of each soft drink in, say, city A with just a much bigger sample size than of any soft drink in sample C, but that's just due to the bigger sample size. So how do I kind of scale out the fact that my sample sizes are different sizes? Well, I can divide by the sample size. I can put everything on a relative scale, present percentages instead of frequencies. Kind of nicely enough, the graph almost does this for us, right? The histogram almost does this for us. If we were looking at three histograms kind of side by side and we scale them to the same height. However, if I use the more complicated type of histogram where I might have the blue bars representing the frequencies from city A, and maybe I'd have red bars right next to them. Maybe I shouldn't call them city A or whatever, but city number one. So like right next to the blue in this A class, I have a red bar that represents the result from city number two. And right next to that one, I have a yellow bar that represents the result from city number three. And I have the same setup for answer B or answer C or whatever. I have the three cities next to one another. One. Now, if I'm reporting raw data, I might have I will have the city with the really big sample size is going to have a really tall bar. In every one of these, it's going to dwarf the city with the smallest sample size simply because it's the largest sample size. I don't really get a lot of information about what's going on from that graph. But if I set everything on a proportional scale, that would be a much better way to compare those three different cities that have three different sample sizes. So there are costs and benefits to either direction we choose to go. And another advantage is so percentages are essentially always between 0 and 100, right? In this context, we're always between 0 and 100%. And people are just used to dealing with numbers that are like on that scale. If I have a data set of size 30,000, people just don't deal with numbers that are like 15,000, 25,000, 30,000 very often. It's just a little less intuitive, right? Our numeracy, our ability to just understand and interpret data that's presented to us pretty readily and accurately is just a lot better for numbers that are like 0 to 100 than numbers that are like in the 10,000s, or certainly numbers that are in like, the 10 to the 20th place or something like that. If we're like, talking about the, distance to the nearest star or whatever in meters or something, or like the 10 to the -6, like, if we're talking about the sizes of different cells or something. We're just not used to looking at numbers that are on those scales. So there's a benefit to putting everything in percents that it kind of scales everything to numbers that we're looking at all the time, 0 to 100. And I should say that some of these disadvantages can be mitigated. For instance, if I were to present this relative frequency graph, and maybe somebody argues, well, hey, I don't know what the sample size is now. A lot of times you'll just see like actually physically on the graph, just like in one of these spaces between the lines or something, they'll put like n equals 25 or n equals 457, just as a little indicator that, yeah, we're presenting proportions, but here's the sample size. So not saying that these issues can't be mitigated. Sometimes they sometimes can. Any questions so far? Okay. Let's take a look in these next two slides at distribution shapes. So we have these grouped into kind of two different categories here, bell shape, bimodal, and uniform. And then on the next slide, talking about skewedness, right versus left skewed. So these, again, this is kind of a human level classification. There's some gray area here, but these are words that we might use to describe kind of the shapes of histograms or the shapes of the graphs of data. And the first one, geez, every time I do anything on Microsoft, it pops up and has to tell me something urgently, and I have to click got it so that it knows that I've validated the Microsoft programmer who, probably spent 100 hours putting some goofy tool in that I'll never use. So anyway, so if I'm looking at my histogram, and if I see something that looks like this, And I don't know why my bars are leaning like the Tower of Pisa, but they are. So sorry about that if that's bothering you. If I see something like this where I have a clear peak in the middle, tailing off to the sides, and there's kind of this like axis of symmetry. If I look at the middle and I imagine flipping the whole thing over that middle axis, it would kind of look the same. So if I flip the whole picture over this kind of middle axis, this peak, it kind of has the same shape. That's what we call a bell-shaped distribution. So this is bell-shaped, often also called normal. The normal distribution, something that we'll talk an awful lot about in chapter 6, and we'll use pretty much in every problem from chapter 6 on in the course. Sometimes also called the Gaussian distribution. So we might say this looks Gaussian. That's referring to Carl Friedrich Gauss, a mathematician, who, uh, let's just say, who's accredited with a lot of important discoveries. Historically, it's a little hard to say, whether somebody actually discovered something themselves or whether they were accredited with it sometimes because, it was a lot harder to get things published back then. And somebody who just found a cool result and wanted it published might send it in and say, "Hey, I'm Gauss, you should publish this." And they'd say, "Oh, we're going to publish this because it's from a famous person." So, but so Gauss, did a lot of important math and was accredited with a lot of important math. So that's the bell-shaped distribution. Typically, when we draw distributions, we just draw like a line graph representation, so something like this. And I think it's also important to note that, this or this is kind of some kind of like theoretically perfect version. It's some kind of like Platonic form of the distribution. But if we actually looked at real world data, even if it came from something that followed perfectly a normal distribution or a bell-shaped distribution, what would the actual histogram look like? It wouldn't look perfect, right? We might get a little lower frequency there than we expect. We might get a little higher here than we expect. Right, so it's not like this nice, perfect distribution. We still see those same characteristics popping up. A peak in the middle, tailing off to the sides, and kind of a rough axis of symmetry. If we flip the whole picture over this axis defined by the peak in the middle, it looks about the same. There are a lot of things that naturally turn out to be bell-shaped, normal, Gaussian. So things like IQ, things like height or weight, uh, things like SAT scores. There are a lot of characteristics that turn out to be Gaussian. Why is that? A little bit of a spoiler here, but in chapter 6, we'll see that we have this really important idea called the central limit theorem. And roughly speaking, what the central limit theorem says is it says if we average together lots of small influences, the result is something that looks like a normal distribution. So when I have a characteristic that I'm measuring, and that characteristic is the result of lots of small influences kind of combining together, and I kind of average those all together or accumulate them all or add them all together, then the result is going to look like a Gaussian, going to look like a bell-shaped curve. We have this idea of a bimodal distribution. So bi, like bicycle, like two, and mode, it's kind of related to the, sorry, allergies are bothering me. Kind of related to the idea of like middle or mean or median. So mode, there's kind of like the middle here, the thing that's most likely to happen. And there is two of them. A bimodal distribution has kind of two clear, well-defined peaks in the graph. So I kind of lied a little bit in the previous one. If we look at heights and weights, well, most people's heights and weight, for the most part, are determined by combining together lots of small influences, maybe genetic, maybe environmental, whatever it is. But there's one big influence that kind of splits the population, and that's sex. So males versus females, right? Males tend to be substantially taller than females. So where do we see bimodal distributions? When we kind of have a population that maybe has, say, two normally distributed subpopulations aggregated together, right? Maybe we see something like this. We see like the females versus the males here if we're measuring height. And when we aggregate them together just as all people, we might see these two peaks from the two different sexes, different heights. But this idea of a bimodal distribution is one that comes up on occasion. Exam scores tend to occasionally be bimodal, especially on challenging exam. There's kind of, the students who put in the time and effort, who maybe get the kind of ABC range. So there might be like a spike at the kind of B range, let's say. And then there's the students who, let's just say, maybe forgot about the exam or didn't really study for it or whatever, that do fairly poorly. So, that's something that you sometimes see in grade data. If there's a clear split between students who maybe didn't put in the effort versus those who did, the lower grades versus the higher grades, and we actually kind of see that a little bit wherever it was. I'll just use this as an example, but kind of see that a little bit here, that there's like this kind of group, this subpopulation of the ABCs, and then there's another group of the Fs, and that can be somewhat typical in exam data, depending on the type of course. A stats course like this is, it is intended to be a little less challenging than some other courses, just because it's not really a major course, right? It's not like a calculus course or something like that, where it's really a program specific course that a high level of mastery needs to be attained. So, so maybe a stats course like this, don't worry that if you study 10 minutes too little, then you're going to end up in the F category. That's not likely to happen in a course like this. But again, so bimodal might be something like a situation where you have one big variable that's kind of splitting some subpopulations out, but then there's a bunch of smaller variables that are combined together to get kind of normal looking distributions, but in two distinct areas. And then uniform distribution just straight across. So one example is sex. So say male versus female, there's about a 50-50 split. It's about uniformly distributed. If we made a histogram for number of births this year that were male versus number of births that were female, it would be pretty close to equal. A lot of times our uniform distributions come from kind of human created things where we really try to make things uniform. So maybe something like a die roll. If I roll a die 100 times, even if it's a fair die, I'm not going to get exactly equal amounts in each of the bins 1 through 6. Of course not, because 6 doesn't go into 100 evenly. But I should get pretty close to 1/6 of the data, 16, 17 rolls in each of the bins. So a die roll might be an example of a uniformly distributed variable. Or things like a roulette wheel, or things like drawing a card out of a deck. the chance you get, hearts versus spades versus clubs uh, would be equally likely. So a lot of things, a lot of examples of uniform distributions are things that we have created with the intention of making a uniform distribution for gambling or for games or whatever, but some of them come out naturally. Then we have the ideas of skewedness, right versus left skewed. So skewedness relies on this idea of an outlier. And outlier or outliers are simply data points that don't fit in with the rest of the data. At this point, we're just going to kind of leave it at that. In chapter 3, we'll look a little more in detail at outliers, maybe come up with um, kind of a more formal definition or a more mathematical definition of what we're going to call an outlier. But for now, it just kind of doesn't fit in. Right? So if I have a histogram that I draw out and I get a really nice distribution over here, most of my data is just kind of in this general vicinity over here. And then I get one data point over here and one data point over there. I think very few people would argue that these are not outliers, right? These just don't fit in with where the vast majority of the data seems to be sitting. They're kind of way off here out to the side. So if I draw my histogram out and I see that there are some outliers, I might ask myself, well, do those outliers tend to be to the right side of where most of the data sits, or do they tend to be to the left side of where most of the data sits? Do I tend to have a situation like this, or one like this, where my outliers are to the left? Note that these are not the only two situations. There's also a third situation, a third possibility. Maybe I have some outliers on both sides. So maybe there's some symmetry in my outliers. I have some on the left, but also some on the right to kind of balance it out. This would be symmetric. This would be not skewed. However, if we're in the situation where our outliers tend to be heavily biased toward one side or the other, then we have some skewedness. The skewedness is in the direction of the outliers. So if I have outliers to the right, then I call this right skewed. So I have a couple of data points that don't really fit in with the rest of the data, and they tend to be on the right side of the data, or in other words, associated with higher values, higher data values. Clearly, if we're saying there's something to the left and something to the right, we're presuming a natural ordering or ranking here. So we're presuming some structure here that being to the left or right has some meaning, right? It's not just like your favorite soft drinks and we have whatever these 10 selections and it just so happens that the way we ordered them that 1 through 5 people really like and then number 9 people also really like. Well, that's not skewedness, right? That's categorical. There's no rhyme or reason to that ordering. We could have just as easily um, you know gotten a popular soft drink, say, in every other slot or something like that, every second slot. So we're presuming that there's a natural ordering or ranking to our classes, our bins, to our data. So we're presuming some amount of structure here. And likewise, if I have my outliers off to the left, we will call that left skewed. Right skewed data comes up often in economics. So you might see things like income being right skewed, right? There's a lot of people who make in, say, the $20,000 to $100,000 a year range. But then there's a couple people like, Elon Musk or somebody like that who makes way out here to the right. There's not really people balancing them out. There's not somebody who makes, whatever, negative $5 billion a year or something like that. But there might be some people who make positive $5 billion a year, depending on exactly what you're talking about when you say income. As a result of that, things like net worth, right? Just kind of like how much savings you have essentially. Um, so net worth would maybe also be right skewed. And then things that are goods that people can reasonably spend lots of money on. Maybe reasonably spending lots of money is a bit of a contradiction in terms, um, but like you can't buy $30,000 roll of toilet paper. At least I don't think you can. Uh, but you can buy a car that's super expensive. Most people buy a car that's, I don't know, $5,000 to $30,000 or something, but there are cars that are like a couple $1 million. So things like cars, houses, not hoses. I don't think you can buy a super expensive garden hose, but houses, right? House prices, like most people are gonna buy a house that's like, I don't know, 100 to $350,000, but there are some mansions that are like $5 or $10 million. So because of the right skewedness of maybe incomes and net worths, some of these goods where there can be a luxury component to it also have some right skewedness to them. So often in economic data, if they're looking at income or net worth, something like that, or even maybe housing prices in an area, we might choose to represent the kind of typical or the measure of center, the typical data point, using maybe a median instead of an average. We'll see a little more on that in chapter 3, but when we know that there's some skewedness involved, we might want to be careful about what measure of center we represent. So often in economic data, you'll see them talking about median income or median net worth or median house price. And there's a good reason for that, because when we're asking what's the typical house selling for, or what's the typical person working in this job making, we're not really interested in the top 1 or 5%. We're kind of interested in maybe the middle 50% or the middle 70%. What do they look like? And the median does a better job of that than the average. Left skew distribution is a little hard to come up with kind of reasonable examples, but probably it's slightly morbid, I suppose, but probably the most common example is age at death, right? So like most people live to, let's say, like 60 to 80-ish. There might be some people who live a little longer, maybe to 90 or 100. But there are some people who die in their first year of life or their second year of life. It's not common, it's pretty rare. But there are some people who die, let's say, 70 years younger than expected, but nobody lives 70 years older than expected, right? Like essentially nobody lives to 130 or 140. So that would be a left skew distribution. There might be some outliers on the right, but there are many more outliers on the left. Now, a little side note, if you get so many outliers in an area that it like makes up its own population, their own subpopulation, well, it's no longer a set of outliers, right? Now it's kind of bimodal. So there's this kind of fine line that, we can have outliers on one side or the other, but we can't have too many outliers or they kind of cease to be outliers if we have a bunch of outliers in an area. That's just a subpopulation. Okay. That's an important idea in ANOVA, the analysis of variance that we'll talk about at the end of the course. I think that is all that I have to say on this. Oh, a symmetric example where we have outliers on both sides, stock market data. Stock market data. Um, you can really start splitting hairs here, but I think it would be reasonable to say that stock market data like rate of return, say annual rate of return, annualized rate of return, say day to day on the stock market, something like that, is going to have outliers. There are some days that the stock market just does really good and some days that it's very crashy. Most of the time it does kind of about average, but these outliers are kind of on both sides of the fence here. Any questions on any of this? All right, let's look at some other types of graphs now. So an example here is a time series graph. It looks like a bar graph or a line graph, something like that, but our horizontal axis down here represents time. I suppose you can kind of argue that it's a histogram, just where your bins are like this year or that year or some other year. But really, this has a fundamentally different feel than a histogram. Instead of like, making bins that are like different heights or different grades or something like that, we have a progression of time. So a lot of examples here come from finance or economics. You see unfortunately, Gallup doesn't publish this anymore. At least I can't find it. It's at least not out there for free. So this is from back in 2010 to 2015. But we have unemployment and underemployment being reported here, as well as payroll population over time. So each day, Gallup, a company that does polls, will call a certain number of people or query a certain number of people and, you know, see who's unemployed, who's underemployed. Um, they'll record that data point, and this is a progression over time for that couple year period. And we see that, I mean, it doesn't look very visually stunning, but we do notice if we look carefully that at this, say, 14 line here, uh, that the graph above it is getting closer to it, it's coming down, and the graph below it is getting a little further away from it over time, it's going down as well. So over this time period, seems like unemployment and underemployment were decreasing, not very rapidly, but decreasing a little bit at a time. Again, I think a line graph is good here because if I know that the unemployment rate is at a certain number today, it's probably going to be about that number tomorrow and the next day or the next week. I'm not expecting if it's 6% today that it's going to be 3% next week and then 10% the week after that. So I expect there to be kind of a close tie from one data point to the next. So I kind of indicate that with the line graph. We, of course, have stock market data like, say, the S&P 500. This GSPC is the S&P 500. And looking at this line graph here, don't worry about this red and green stuff on the bottom here. That's just trading volume, but focus on the blue graph here. Again, this was from that same time period going up to 2015 and starting back here in about 2007. We have a big crash and then a long, steady recovery. And that's pretty typical of crashes, right? You don't sell at the bottom of a crash because then you miss out on the big recovery. You would have, bought high and sold low, and that's the exact opposite of what you want to do. Or here's a different perspective on it. One thing that's really interesting is in a time series graph, I'm quite often in the position where I need to choose what time I want to represent. The story that this tells is, hey, look, there was a nice strong market, just steady growth from 2009 to, say, roughly 2015. That looks really nice, right? That tells a very different story than if I go back a couple more years, that there's a crash, and then it took maybe 4 years to grow back to the level that we were before the crash, and then a little bit of growth after that. Where do I chop off my data? right? I think it's always, if you're presenting data like this, it's always worth asking yourself, if I went, 25% earlier or 25% later on either one of my endpoints, would that really qualitatively change what I'm presenting here? And I think it's fair of you to ask that of somebody else presenting. Okay, you chose these these endpoints. Why did you choose those endpoints? And what would the picture change if you went, a little earlier or later on either of those endpoints, right? This tells a very different story than this does. Here's another XKCD comic, just a, a joke about if you're in computer science, the odds that some word you'll type will start with a weird symbol. So like C++ and Python are pretty like, they almost seem like you're just typing a language, you're using normal words and all of that. But if you've ever typed anything in like Bash, like shell scripting or Perl, it's kind of I don't know, a little crazy to work with. So any questions so far? All right, so moving on to another one of the more popular recognizable types of graphs, the pie graph or the pie chart. And it's nice when we want to present data as parts of a whole. When we want the idea of a relative frequency distribution, but we really want that relativeness to really take center stage. If I make a histogram and just slap percentages on it, I mean, okay, that's kind of nice in some aspects, but the bars are still a little hard to compare to one another, to compare to the whole, I should say. But in a pie chart, I can really see very quickly. This is something that our IT department sent to us once several years ago from our spam filter. I don't, they sent it to us like once or twice and then never again. So I don't know if we got a different spam filter or if people were complaining about it or what. Or maybe they're still sending them and they're getting caught in spam. I don't know, which would be kind of ironic. Um, but anyway, I kind of like this example because you can see really at a quick glance, there are three things that are each making up about a quarter of whatever is going on here, and about two things that are making up the other quarter. So I see that block connections, which is probably if you're trying to go to some sketchy website, that's about a quarter of what our CCAC spam filter at that time was filtering out. Light blue and dark blue, spam medium and spam high, or about 25% each. And together, the spam medium or high accounted for about half of what the filter was doing. And then these other two that kind of combined make up the last quarter or so are bulk messages. So basically, probably we'd consider just general spam messages, and legitimate, where the spam filter says, I think this is a questionable message. And you go in and you say, no, that's actually okay, let it go. Um, so, this is a good example of a pie graph being used well. I can look really quickly and see there are three things that each make up about a quarter of what's going on, and two things that comprise about that last quarter. So one of the important things with pie graphs is really the coloring, right? That's kind of, I mean, I suppose you can get around the coloring if you wanted to label these like 1, 2, 3, 4, 5, but coloring, I think, is an important component of pie graphs. This was these next couple pictures were taken from a a professional polling company. It was either Rasmussen or Pew. I forget which one it was. I think it was Rasmussen. Um, and I actually read this report and I was really surprised at how terrible these graphs were. So the first thing, you look at this graph and you see, okay, are you happy with your job? Yes, no. I look at the histogram. Okay, most people are happy with their job. Yes is blue. I look over here and I see, wait, why did blue go from the majority to, about 25%? This is kind of confusing. Oh, wait, well, blue is yes in both cases, but they kind of switched the like, I don't know if you call it parody or something of the question. Are you happy with your job on the left versus are you worried about losing your job on the right? Well, if you're worried about losing your job, you're probably not happy with your job and vice versa. If you're happy with your job, you're probably not worried about losing it. So, if you're going to use colors, don't just, insist on using the same color for the same answer. In this case, this is very misleading. Uh, Maybe not misleading, but at the very least confusing. Um, because, why is blue so big over here and so small over here? Right? Just use a different set of two colors. If you're going to use colors, think about how your audience is going to interpret that. The whole purpose of the graphical representation is to make it easier and quicker for somebody to digest and to do it accurately. And if it confuses them, or if it makes them, or if it leads them to make a mistake, then your graphical representation has actually done harm. You've taken a step back. You could have just presented the numbers and been done with it and would have been better off. This one I think is even worse. The job market is better, worse, or the same. Blue is better, red is worse, green is the same. I would have thought like green would be better and blue would be the same maybe, but whatever. Okay. I mean, um, so okay, so we have these, and then we have these concentric rings representing different age groups, age 18 to 39, age 40 to 64, and age 65 plus. So these are kind of pie graphs here, this better, worse, or the same, but it's like a concentric ring kind of thing. It actually makes it kind of hard to tell the proportion of people who think that it's worse because the starting and ending points for worse are all at different points. So like, are the middle-aged folks, do they think that it's worse than at a higher prevalence than the younger folks or than the older folks? It's hard to tell. It's also kind of misleading because when we look at a two-dimensional color thing like this, we look at just kind of the amount of color that pops. And the outer ring, because it has a larger diameter or circumference, it just naturally has more area than the middle ring. And the inner ring, it isn't really a ring, it's kind of a whole wedge of a circle. So it's really hard I don't like these consecutive or concentric ring pie charts at all for all of these reasons. But at the very least, if you're going to use it, maybe look at the two things that people think are going to think are the most important, say better and worse, put worse down at the bottom so that at least it's, all of it, it's aligned on one side. Um, oh, and again, making it even worse. I don't know who wrote this, but who wrote this article, but it was not a good article. Um, Over here, a year from today, unemployment will be higher. Presumably, these are the people who answered affirmatively and didn't really say that, um, but now the different age groups are what are related to colors. Where over here it was better, worse, or the same were related to colors, and ages were concentric rings. So, the story here is if you're going to use a graphical representation, especially if you're going to use a more complex one that involves colors and all of that, make sure that it actually does something positive for your argument. I think this person just downloaded a new version of PowerPoint or something or Excel and was really excited about all the new features or something. I don't know, and just tried to use everything all at once. I don't really know what's going on here, um, but the graphical representation should benefit the presentation, not be a detriment to it. If it's confusing people or if it's, if you're using the same colors to mean different things, you might be better off just presenting the data in a table or something. So here's a little joke. The percentage of the chart which resembles Pac-Man is a pie graph. Another thing that especially these days with more technology is becoming more prevalent, and I think is a really good thing, again, when it's used well, is the idea of a heat map. We already kind of saw this idea in the US states growth or decline by year, where the darker the red was, the bar was, the more growth we had, and the darker the blue was, the more decline we had. And that's the idea of a heat map, is we're taking kind of some kind of natural color scale, often blue to red, with blue kind of feeling like cool and red feeling like warm. So there and gradations in between, like yellow kind of in the middle. So what heat maps do is they take data like this, for instance. This is the number of opponent rolls that it would take you to pay back your investment in a certain property or putting a house on a property or whatever in Monopoly. So lower numbers are better for me. Fewer opponent rolls for me to make back my initial investment is a better result than taking more opponent rolls. So the lower numbers here are more red and the higher numbers are closer to blue. So we see buying the first property in Mediterranean or Baltic, not a very good investment because it takes 1,000 opponent rolls for me to recoup my investment. On the other hand, say putting a hotel on, what is it, St. James, Tennessee, or New York, that's probably a pretty good investment. Or buying a fourth railroad, if I already have three, that's a really good investment, right? So this heat map lets me see pretty quickly, what are the darker red um, areas? Those are the better investments. What are the more blue areas off to the left here? Seems like buying the first property is kind of never a really good investment, but you're taking that bad investment so that you can get the monopoly on that block and start building houses. Um, I don't know. When my sister and I would play, we never had the patience to actually play by the rules and try to get a monopoly on a block before you start building houses, which is how it's supposed to work. So it was just kind of like, oh, well, you can build a house on any property you own, and so we didn't exactly play by the rules. But apparently, if you play by the rules, it's a much better game. There's a lot of trading and trading of properties and making deals, and I think maybe even if you like land on a property and you don't want to buy it, you're supposed to like auction it to the rest of the table. So yeah, there's all kinds of rules that, but I don't think anybody actually plays by the official Monopoly rules. There's probably more house rules than real rules. So here's another example of a heat map. This is from the Heritage Foundation. They publish something that they call the Index of Economic Freedom. And at least on the basis of this index, we see the freer the country is in terms of economics, the more green it is, and the less free it is, the more red it is. And they color in each country according to their in, according to their index, according to their measurement on this scale. So we can look across the globe and pretty clearly just pick out if there's a country you're interested in, you can pick it out and see kind of where it falls in the scale or where it falls relative to other countries near it or other countries across the globe. Um, so that's kind of an example of a heat map. The US used to be dark green, and in recent years, it's become a little more light green. I think it's a little harder to get the dark green designation these days. Or here's an example from the Bureau of Labor Statistics. Uh, whatever field you're looking to go into, this is a good resource to look at for your career. If you go to the Bureau of Labor Statistics, pull up the career that you're looking at. So here's an example for registered nurses, but pick whatever career or careers you're considering and look at, what's the salary that you can expect? What's the job demand? Do they expect that there's going to be a higher demand in the next 10 years or that the demand's going to be going down? It's going to be harder to find a job in that area and so on. But we look at the scale up here and we see that lower numbers are associated with lighter blue, higher numbers, higher wages are associated with darker blue. And I can see kind of a cluster in the kind of Midwest area here with a bit lighter blue going out to the coast like New York, um, the Northeast, on the West Coast, Alaska, Hawaii, darker blue, those are higher wages. So I can see pretty quickly where the higher wages are. Interestingly, Minnesota is kind of on the higher end. I think the Mayo Clinic might be in Minnesota, but I kind of doubt that one hospital system is going to be that impactful for all of the nurses across the state. But um, so yeah, we can tell a lot on the basis of just this picture. As kind of an aside, is it worth it for you to say, oh, I'm going to go to New York because I'll make more money instead of staying in PA where kind of on average I'll make less money? Well, you have to consider cost of living as well, right? So in especially say New York City, cost of living is very high, or like in Los Angeles and California, cost of living is extremely high. Uh, so you have to balance the cost of living in that area with the wages. The wages might be higher just because they need to support the higher cost of living, and really you're kind of no better off. Or you might be able to go and get a higher wage um, in an area that has kind of the same cost of living and actually be a lot better off. So always balance the wage that you're being offered against the cost of living in that area. Okay, any questions to this point? Okay, so our last couple of slides on types of graphs. We won't quite get to the Excel demo today, so it'll be one of the first things we do next time. And we'll probably also talk about bad graphs at the beginning of next class as well. But the next topic we're going to introduce here, the next type of graph, is a scatter plot. And this is a bit different than our previous graphs, right? If we have a histogram, we have our variable classes and we have frequency going up the ladder here. Or if we have a pie chart, we have classes, say A, B, C, and their proportion of the pie is in line with their relative frequency. So I have one variable that I'm describing here. In another scenario, I might have two variables. And in particular, two variables that are coupled. So I have maybe person one from my sample. I might record their height and also record their weight. So that height and that weight for person one are kind of inherently connected. And then for person two, I might record their height and weight as well. And so on, maybe down to 100 people. So I really have each of these as like an ordered pair, right? Person one's height and weight kind of inherently go together, as does person two's height and weight, and so on. So I could think of this ordered pair, maybe the height is 60 inches and maybe the weight is 120 pounds. I could look at, or let me write these the other way, height and weight. So I could have a measurement of 60 on this height axis and a measurement of 120 pounds on this weight axis, and there's my point 60, 120. This point here represents the information, the data associated with person one. So this is associated with person one. Maybe person two, maybe their data point is like here, and maybe person three, so that's person two, and maybe person three is up here somewhere. And if I do this for all 100 people, right, maybe I get something like this. So this would be a scatter plot. I'm putting just the point, each of those points at a location that is associating two variables together. And then I represent all of my data with just a bunch of points. And I might be interested in, say, asking the question like, does it kind of seem like people who are taller tend to weigh more and people who are shorter tend to weigh less? Well, that maybe does seem like the case here. Or if I wanted to draw a line that was a model of this data, I might note that that line maybe has a positive slope. That if I know that somebody is a bit taller, then I would predict or I would estimate or guess that their weight is a little bit higher. So here are some examples of scatter plots. Keep in mind we're comparing two different variables here. So here I have 4 scatter plots. This would be the output of a flow cytometer. If you're interested in medicine, it's a really cool technology to look up. Essentially, what's happening here is that if you look at our cells, we think of our cells as these like little, almost like soap bubbles or something that are just like smooth, but really our cells have all of these little doodads poking off of them, these little proteins that do things. And that's what these are looking for. So how the flow cytometer works is you have an antigen, you put an antibody into the mix of cells that you take out of somebody. The antibody attaches and it has this little fluorophore deal at the end that kind of emits a certain frequency of light when it's hit by a laser. You take each of these cells, like this might be cell number 1, and maybe it's emitting some amount of blue light when it's hit by a laser. You flow the cells, like cell 1 here, through a tube, you shoot it with a laser, and you see what intensity of the different laser lights you get off of that cell. So, this protein here might be what we call, say, maybe CD19, cluster of differentiation 19. If our cell is expressing that protein really strongly on its surface, that might lead us to believe it's a certain kind of cell, where if it's not expressing that at all, we might think it's a different kind of cell, or maybe we think it's cancerous versus non-cancerous on that basis, or something like that. So that's what these are representing. So we take cell number 1 and we look at, what is its CD19 expressivity versus its CD34 expressivity. Maybe that's this guy over here. Is it expressing CD34 or not? Or is it expressing it at a high level or low level? And then I plot for each cell, I plot a little dot here. And you can see there's like thousands of dots. So we do this with lots and lots of cells. And I look at the scatter plot, and maybe the physician, the pathologist, is looking in this box here, and they're saying, if I see a lot of cells in that box, that tells me something. Maybe that makes me suspicious for AML. Or maybe if I see a lot of cells in that box, that makes me not suspicious for some other disease. Or I can compare, say, CD13 with CD34, 2 different proteins for the same cell. I could look at this scatter plot, and I see a lot of cells that are in this box. And again, that might tell the pathologist or the oncologist something. Or I could look at CD34 versus an IgG antibody. Or this forward scatter versus side scatter. So that is like our cells have little things inside of them, little organelles, and when we shoot a laser at the cell that will go through the cell wall, it might hit an organelle and get kind of scattered off to the side. Or if it tends to not hit anything, it'll just go straight forward. So the less complex the cell is, maybe like, say, a red blood cell that doesn't have a nucleus, maybe you'd expect more forward scatter, the light to go straight through it, where more complex cells, you might expect more side scatter. So again, that might tell them something, right? So this is what a pathologist or an oncologist would look at, this reading from flow cytometry and along with these gates, and they would say, okay, on the basis of this and the clinical presentation and everything else, I think this person has this disease, and maybe we'll move forward with this treatment, or maybe we'll order these follow-up tests to confirm or something like that. So this is a real practical example of how scatter plots are used in really important and meaningful scenarios. Just another example, a little more colorful. This scatter plot, you can see that, I mean, they've added some coloring later on, but you can see that like down on the left here for the side scatter versus forward scatter, it's just kind of a mass of black dots. It's a little hard to tell, like, are there a bunch of dots here or are there really a bunch of dots here? If we color the dots so that the redder they are, the more dots there are in very close proximity to it, we can tell whether there's just a bunch of dots, like say down here on the left in CD4 versus CD8, two types of immune markers. Down here on the left, there's a lot of cells, but up here on the top left, there's a lot of cells right in this little red spot. So again, coloring can really add another layer that can be really beneficial in some areas, if it's done well, of course. And I think it's done well here, of course. And here's a scatter plot that came out of a paper. This was it's an older paper, so it's not really the best picture. So sorry about that, but you can see that on this scatter plot, if you look at kind of the top right, you see they're actually kind of like triangles, in the bottom right, they're diamonds. So this is comparing two subpopulations, people who are, quote, normal and people who have rheumatoid arthritis. So we see the RA folks, as we move to the right, as they get larger cross-section area of their muscles, we think that would make them stronger. Their grip strength doesn't really go up very much compared to normal patients who their grip strength goes up a lot when they have bigger forearm muscles. So the rheumatoid arthritis is really affecting their grip strength, and making their muscles stronger isn't likely to bring them a whole lot of benefit, right? It's not a muscle issue, it's an issue with kind of the joints and other structures. Okay, I think we will leave off here. We'll talk briefly about log-log and semi-log plots next time and pick up on these last couple of slides, as well as doing our Excel demo next week. Are there any questions on anything from today?